Okay, so now we're going to do our last example. We need to find what f prime of x is and use it to find the equation of the tangent line to this particular function when x is equal to 1. And then after that, what we want to do is find the x values for where our function, our original function here, has horizontal tangent lines. We have a lot of different things that we need to do, so let's just go ahead and get started here. So the first thing that we want to do is find f prime of x. Okay, so to do this, of course, we need to take the derivative of this function. We know that this is a composition function because we have a function stuffed into another function. And to be specific about that, the function 1 minus x squared plus 2x raised to the fourth is stuffed into the function natural log of x. So everything that's inside the natural log function here, that particular polynomial, is what's going to be called the inside function, and then the natural log is going to be what's going to be called the outside function. Okay, so from here, what we'll do is just take the derivative of this, and this time I'll be using Leibniz notation so you can see how it looks that way, and then from that we'll find out what the y coordinate is at this particular function so we can have our point, evaluate our derivative at 1 so we can find our slope, and then from that find the equation of the line. So to take the derivative of this, I'm going to write it as a derivative of f with respect to x. And so I could rewrite it this way. And of course, when I rewrite it this way, I know that one of the things that I can do is I can take the inside function and write it as u. So I'll come over here and say u is going to be this. And so if that's the case, then we know that f can now just be written as natural log of u. Okay? So from here, we will say the derivative of u, and of course, f is now natural log of u. The derivative of u with respect to x would just be all of this. And so now what we'll do is just take the derivatives of each of these. So the derivative of natural log of u is just 1 over u. The derivative of 1 minus 2x squared plus 2x raised to the fourth will be 0 minus 2x for this term plus, yep, that's right, 8x to the third. And then if we simplify, we know that our u is the same as 1 minus x squared plus 2x raised to the fourth. So we will just replace it with that. And so this is our derivative. So what we're going to do next is, now that we know what our derivative is, we will take this and evaluate it at 1 to find out our slope of the tangent line. And then we will take 1 and put it into the original function to find the y coordinate for the point in which the tangent line goes through. Okay. So from here, we know that f prime of x is just 8x cubed minus 2x, all that divided by 1 minus x squared plus 2x raised to the 4th. So I'll go ahead and get rid of this. And so now we need to find the slope of the tangent line, which is just going to be f prime evaluated at 1. And we need to find out what f of 1 is so that we can have our point. So if we take this and evaluate it all at 1, we'll see here that our first term in our numerator is just going to be 8 minus 2. Of course, 1 minus 1, which ends up being 0. And then 1 to the 4th is 1. times 2 is 2. So we just have 0 plus 2. And of course, that ends up being 3. So the slope of the tangent line is equal to 3. So now we need to find our y coordinate to go along with the x coordinate so that we have our point. So if we go in and just plug in this into the original function, you'll see that, of course, this ends up being 0 again, and all this just ends up being 2. So we have a natural log of 2. So when x is 1, our y coordinate is natural log of 2. And so from there, we'll go ahead and find the equation of the line. So from here, we use the point slope form of an equation of a line where this is going to be our x1, this is going to be our y1, and of course this will be our slope. So if we go and plug in everything, natural log of 2 goes here, 3 goes here, and 1 goes here. And so from this point, all we need to do is just solve for y to get it into slope-intercept form. So we'll distribute, and then after that, we'll add natural log of 2 to both sides. And so our answer will end up being 3x plus natural log of 2 minus 3. So this will be the equation of the tangent line. Okay? All right, so the last thing that we're charged with doing is actually finding out when our original function has horizontal tangent lines. Well, we know that any horizontal line has a slope of 0. So here, if the tangent line is 0, then that means that the derivative of the function has to be 0. And so the x values for where that happens is what we want. Since we know that the derivative of the function is just 8x cubed minus 2x all over this fourth degree polynomial, we know that this is a rational function. Since this is a rational function, the way that we find out what the zeros are for the rational function is we look at the numerator. Whatever values of x make it 0. So we just set this equal to 0. And then from here, we can factor out a 2x out of each term. So we have 4x squared minus 1 equals 0. And then from here, we can break this out and say that 2x is equal to 0 or 4x squared minus 1 is equal to 0. Of course, here we divide both sides by 2 and get x equals 0. And here, this is the difference in two perfect squares. So this could be written like this, which means that we can further factor this out to 2x minus 1 times 2x plus 1. And of course, if we solve all this, we'll say that 2x minus 1 is equal to 0, or 2x plus 1 is equal to 0. And so from that point, if we solve this equation, we'll get x is equal to positive 1/2. And if we solve this one, x is equal to negative 1/2. And so here are our other two x values. So what this means is that for our function here, the way that it looks, it's either going to have something like a peak or a dip or something that looks something like this at these particular x values.